Okay, before I actually start working out the control formulation, I just want to get a quick student feedback on were you able to do the PID control lab on your own from the TC lab? Were you able to get good results or acceptable results?
So the videos said that from the lab showed how to do.
Okay, I will discuss that in today's class. That's totally fine. Actually, if you want, what we can do is in the lab session of today's class, I would actually go through the problem and then discuss how do we get the actual PID coefficients for a practical system. Any questions from my online students? Okay. Now, in today's class, what I want to do is I want to go to the very basics of PID control. And even though PID control is used widely, the key question here is why does a PID control work? What does PID control do to a control system? Now for that, I'm gonna go back and actually do something for review. So let's understand that we have a system. Okay, we have a system. This is an open loop system. So I'm going to call this G of S. And why do I call it a G of S? Because I'm expressing this as a transfer function. Now what I would do is I would tap the output. I would tap the output. I would feed that through some type of feedback. And it could just be a unity feedback, which means your output is not conditioned. Sometimes what you want to do is the output, maybe you take the successive difference. In other words, you differentiate. Sometimes you integrate the output. Then what we have is we have a summing junction here. This output, the sample of the output gets fed into the summing junction. And this summing junction is where our input is coming in. So we have this input, and here we have this controller. And this is the output. And I'm going to call this output, say, X of T. So this guy is the controller. So what is the first step in controller design? The first step in controller design is to construct a closed loop transfer function. How do we construct a closed loop transfer function? So closed loop transfer function, and I derived this in the class, is something like if you have a feedback, if you have system transfer function, the closed loop transfer function, which means converting this feedback and making this part of the whole thing, becomes GS divided by 1 plus GS times HS. Now this is super duper important. Why is this super duper important? Because remember, at the end of the day, what we want to do is we want to control the system. System is stable only if the denominator of this transfer function doesn't become 0 for certain values of S. In other words, we worry about poles. poles are the locations when the denominator of the transfer function becomes 0. So now we have this closed loop transfer function, which is GS divided by 1 plus GS HS. This is the transfer function, and I'm going to call this as XS, which is the output, XS divided by U of S. Now, what does this controller do to our closed loop transfer function? And I'm going to start with a very simple case. Imagine I'm going to use a proportional control. I'm going to use a proportional control. What do I mean by proportional control? Proportional control means if I sample this x of t over here, what's going to happen is same x of t or x of s for that matter, let me be clear, x of s comes here. And then what I have here is I have the difference here at this point. I have the difference between maybe x of s or u of s minus x of s, which is called as the error term. And this proportional control means I just have a constant k that is multiplying. Then what happens is this k times e gets fed into this transfer function. Now, I can rewrite this whole mathematics something like this. If you recollect, in last class, we talked about the block diagram algebra, wherein which I can combine this k with this g of s. And then what I get is I get this new transfer function. And this new transfer function is k times g of s. And I'm gonna just show unity feedback. There is just one, so I haven't shown the thing, but this is u of s, this is x of s, and then I have this k of g of s. So now my closed loop transfer function happens to be x of s divided by u of s. Please note, h is 1, and this g now became k times g of s. This g became k times g of s. So what has happened, that this transfer function now became k times g of s, 1 plus k times g of s, and h of s is 1. So this is what happened to my transfer function. Everyone clear so far? So this transfer function is what replaced. This is now the closed loop transfer function. So looking at this new transfer function, what this new transfer function did is it changed the zeros and the poles of the system. Can you see that there is this k floating around, which means clearly the poles are changed. Are you with me so far? The zeros are changed. Basically, they are now, it's k times g of s. So basically there is change, and this change is trivial in the sense that this simple gain would actually, if you think about it, if the value of k is 0, if the value of k is 0, which means the numerator of this thing is 0, and then the denominator is just 1. So 1 divided by 0 is 0, and your output is actually 0. So what has happened, with this particular system, with this particular thing, proportional gain, the system dynamics has changed. Now, how does a simple controller, proportional controller, change the system dynamics? And let's take an example. And this is super important. So let's take an example. And in this particular example, I want to basically take the same system that we studied in TC lab. Can someone tell me what was the system dynamics equation when we studied the TC lab? What was the system dynamics equation? Was that first order, or was that second order, or what was the system dynamics equation? If I recollect, it was first order system with dead time. You agree with me? This was the system. So for an example, let's ignore this dead time. Assuming the system dynamics is just first order. Assuming the system dynamics is just the first order. So how would the system look like? So the first order system dynamics would look like something like x dot of t is equal to x of t. This is kind of the first order system. And if you look at the standard form for the first order system, this is something like tau s plus 1. This is the standard form of the first order system. So if you have a first order system, typically the first order system is expressed as tau s plus 1, where tau indicates the time constant. And this time constant is indication of how fast or how slow the system responds. If the time constant is very large, system is going to be super slow. If the time constant is close to 0, system would be quite fast. Now, what I want to do, so what I want to do is let me see, there's okay, so okay, so in this particular system, I'm going to add a controller, and this controller, unfortunately my PowerPoint is not responding. So what I will do is I will try to open a new, so maybe new file. Just bear with me for a second. So new file, blank. Oh, what's going on? Sometimes. Okay, fine. Okay, so what I'm going to do is I'm going to create a simple first order transfer function and add a controller to it. And I add a controller to it. It has a unity feedback. So the feedback is unity. Now what will happen is this system, the first step in block diagram reduction is this system would look like K divided by tau s plus 1. And then we are going to have this branch. U of h. This is negative, this is positive. And the closed loop transfer function, is going to look like GS. Now please note, this is the whole thing is now my GS. My HS is 1. So GS K divided by tau s plus 1 plus GS and HS tau s plus 1.
This K is constant.
Right now K is constant because we are studying the first case, which is proportional control. And I just want to clarify what that means is this error term that is going in, that is just multiplying the value of K, and that term gets fed into the main or the system transfer function, and then you get an output. So now let's try to simplify this further. If you perform the simplification for sake of clarity, I would use this over here. This transfer function is going to look like K divided by tau s plus 1 divided by tau s plus 1 plus K divided by tau s plus 1. Are you with me so far? Next step is I cancel out the common terms, and what happened? All of a sudden, I have this K tau s plus 1 plus K. Do you agree with me? So the transfer function now got changed. Now, what are the poles of the transfer function here? So if you look at the original transfer function, the poles are when s is equal to 0, which means tau s plus 1 is equal to 0. So s is equal to minus 1 divided by tau is the pole of the system. On the other hand, if you look at the system now, what has happened is your pole is s is equal to 1 plus K minus tau, which means the location of the pole got changed. And the location of the pole, change in the location of pole, clearly indicates that the stability properties have changed. So what that means is, initially, if you look at the system dynamics, your pole maybe was somewhere over here. Okay, so this pole is -1 divided by S. And now probably your pole is at some other location, which is somewhere over here, which means the system has become more stable. So you can change the value of K and you can adjust the locations of the pole. And changing the location of the pole would affect how the system behaves to the external input. Say, for example, a step input. How would the system behave if you change the location of the pole? Let me take another example, which is an extension of this example. If I were to add the proportional and derivative control. So same transfer function. Now the second case is I want to add proportional plus derivative. So if I have proportional plus derivative transfer function, I'm going to write this transfer function as tau times S plus 1. And then I have this guy. How does the proportional plus derivative look like? You have Kp plus Kd. So this looks something like this. Kp times error plus Kd times error dot. This is the proportional and derivative looks like. So if you were to write this in a transfer function, it's going to look like Kp plus Kd times S. So Kp plus Kd times S. Now once you add this, this becomes your closed loop transfer function. So now your G of S, if your G of S from the earlier example is going to be Kp Kds divided by tau S plus 1. And if you look at the expression for the closed loop transfer function, what has happened is your closed loop transfer function now becomes Gs divided by 1 plus Gs. This is going to be your closed loop transfer function. So this becomes Kp plus Kd times S divided by tau S plus 1 divided by 1 plus Kp plus Kd S divided by tau S plus 1. And now once you expand, what's going to happen is this is going to become Kp plus Kds divided by tau S plus 1 divided by tau S plus 1 Kp plus Kd S divided by tau S plus 1. Now once again, what I'm going to do is I'm going to cancel out tau S plus 1, tau S plus 1, and try to rewrite this expression something like this. Kp plus Kd times S divided by multiply by tau S tau s kp plus tau s kd 1 plus kp and 1 plus kd times s. So this expression kp plus kds divided by tau s times kp gets added to kp tau kds square tau kds square tau kds square gets here, plus you get kd times s and then kp plus actually kds and kps get added, so we are collecting all the similar terms. So kds square, then tau kp plus kd s plus the last term is kp. Yeah.
So wouldn't there be a plus sign once you substitute, once you denominator?
So did I make a mistake? So let me see. Kp.
And the 1 plus GS.
Yeah. So there will be 1 plus. Correct. So what?
Tau s plus 1 plus KP plus.
Oh yeah. I think I made a mistake. So yeah. Let me rewrite. This will be. Oh, this will be addition. Sorry. Oh yeah. I made a mistake here. Just. Yeah. So you're right. So this will be addition. So this will become. Thanks for catching that mistake. This will become tau s plus 1 plus kp plus kd s. Now I think this is okay. So what you have is you have kd. So kd term gets added with tau and kp term gets added with 1. So what's going to happen is now the system is going to look like kp plus kds, and the denominator is going to look like kd plus tau, kd plus tau, kd plus tau, and kp plus 1. Are you with me so far? So what has happened with a proportional and derivative control? With proportional and derivative control, we change the locations of pole significantly. So if you look at the way the poles have been changed, I can say kd. So here is an s that I'm missing. Kd plus tau s plus kp plus 1 is equal to 0. So now my poles have become minus kp plus 1 divided by kd plus tau. They became my poles. This is the new pole. And that essentially means whatever my original system was is completely changed. Its dynamics has been completely changed. Everyone understood what I mean by that? Now, sometimes it may not be apparent. So for that, what I'm going to do is I'm going to go to MATLAB and I'm going to show you what exactly happens even on a very simple first order system. if we actually add PID control or just P control. So this time, what I would like to do is I would like to go to MATLAB. So if you have access, please open MATLAB. And what I want to do is I want to take the same example and then I want to show you how the system response changes based on the PID control. And with that, then I want to ask you, as MATLAB is opening, can someone please tell me the transfer function? Can someone please tell me transfer function for first order system with dead time? What is the transfer function of the first order system with dead time? It was part of the first assignment. Can someone tell me quickly? Anyone? So yeah, MATLAB is opening up. So can someone tell me what is the equation transfer function for the first order system with dead time? So first order system with dead time transfer function is something like you have a gain multiplied by e to the minus dead time tau d times s divided by tau s plus 1. This is the transfer function for the first order system. So transfer function for first order system with dead time. Now, based on your first assignment, what was the dead time that we determined? Does anyone remember what was the dead time? Tau d. Was it 98 seconds? What was the dead time from your so I'm waiting for MATLAB to open. So please open MATLAB. And let's very quickly look at the response of the first order system with proportional control, proportional plus derivative control, and then we will look at the proportional derivative and integral control. But this is the equation for the first order with dead time. Anyone online students, can someone tell me what was the dead time that we determined for our TC lab, and what was the the time constant that we decided for TC lab? I think time constant was 98 seconds. Time and dead time was, I think, 5 seconds. I could be wrong. And time constant, the time constant is the amount of time it takes to reach out to 66.6% of the total response. So I'm just gonna guess that that time constant was 98 seconds. And clearly, to be honest with you, if we don't remember, we can perform the experiment really quickly and then get this data very quickly. I'm waiting for my MATLAB to open. This is my MATLAB. Yep, it's thinking. So if you have your MATLAB open, please go to Simulink, go to library browser and drag and drop transfer function block. Please go to library browser and drag a transfer function block. MATLAB is not cooperating with me today. So here is what I want you to do till my MATLAB opens. So I want you to go to MATLAB. I want you to go to Simulink and then grab the transfer function block. I'm trying to open. MATLAB is not cooperating with me today. Don't know what the issue is. So what I want you to do is open transfer function block, and let's say my 5s plus 1. And then here, I want you to add another block. And in this block, what I'm going to do is I'm going to add a proportional control. And this say proportional control is just say 5, which is then here you will have negative, you'll have positive, and connect this to a scope. And from here, connect one more thing to the scope. And you're going to have some inputs here. So please add a step input block over here. So please add a step input block over here. And what you should observe is you would, in the scope, you would see something like this, which will be 1. And then here, what you should see is you should observe something like this. I want you to observe this. So how does your output look? So this is the simple proportional control. And what I want you to do is, I want you to change this proportional control from 1, say certain, let's make it very small, say 0.5 to 5. So run this iteration and see what effect it has on your system response. So please observe what does it do to your system response. The second thing, it's a gain block. Yeah. And I'm going to walk around and help the students that are in class. Summing junction. It's constant. Yeah, right now it could be constant. Connect basically just like that. But this is actually, this is a mathematical, you have to add it as a gain. It's not constant. Gain. Gain will have an input and an output. Constant is just the gain. That's the gain bracket. Yeah, that's the gain block. You got it correct. Number of you got it correct. You want to make connections. From here to there, from there to there. What you want to do is you want to have scope block. Step input, and then I want you to observe what happens to the system. And assuming, so can someone tell me what happens as you change the gain? then now you want to pull from here. Now run and check. Now you see that this is the input and this is the response. We need it to reach. Yeah, we need to reach it. This one. What we will do is now please try to change the gain and see what happens. Yeah.
What is the y-axis?
Y-axis here. The one thing that you want to add. Now, now you can see that this one. Now the system response clearly is not reaching all the way. And I'm going here. So now what it means is your steady state error is your point.
Once the system reaches to the
Right.
highest.
This is step. So what you should observe is as you change the gain, your steady state error decreases. Yes, now what I want you to do is I want you to add. So I would take off the gain block. So please take off the gain block and add another transfer function block. So probably what you have is you have this gain block. Please take off this gain block and add another transfer function block.
I have a quick question.
Yeah,
Just wanted to clarify, so gain block, what is it like exactly?
gain block is KP, the proportional control.
Okay, it's the K value.
Yeah.
That adjusts the.
Yes. So
We could like increase the number of the from like 50 and see like the graph.
yeah,
But
so
like, I try 50 and it will be reach the line.
it will reach the line, but may not reach the. There will be some steady state error. And that steady state error is when the value of time becomes infinite. So what you should do is, if you substitute the value of s is equal to infinity, that is what is indicated as the steady state error. And we will look at that. The only point here I want you to understand is if you look at the proportional control, you add the gain, you will still have some type of steady state error. Now let's do this something different. Add another transfer function block here, and in the transfer function block, what I want you to do is, I want you to do something like this. The denominator of the transfer function should be 1, and the numerator of the transfer function should be 5. So alternatively, what you can do is you can copy and paste your code below and remove the gain block and add this transfer function block. So this would be something that can be done. So copy and paste the whole thing, but add this transfer function block.
How can we delete the S?
Okay, I'll show you.
There is another function. You can't delete S from here. If you want to delete S from here, then you have to see. Numerator at 5. Alternatively, take this 0 out. Take that 0 out. Multiply it. One over 1. Change it, and this change the numerator to at 1. And now you will notice this has the exact same effect as the previous gain, right? Because this, what we have is the transfer function representation of the proportional gain. So this is the transfer function representation of the proportional gain.
Now what I want you to do is, I want you to add a derivative term to this guy. So how do we add the derivative term? So add 5 plus maybe 1. So let me show it to you what I mean by that in just a second. So what I want you to do is 5 plus 1s. So in your transfer function block, your numerator will be 1 comma 5 divided by the denominator is going to be 1. So 1 stands for, this would be s plus 5. And this is similar to adding a derivative control. Space.
So yeah, so MATLAB is actually giving you an error saying that it's okay. So please take it out and put a PID log there.
Take it out. Because it's not a realizable transfer function. That's what MATLAB. Just take a PID log.
Don't get it that same definition.
Put a PID log there. And in PID log, let's say proportional is 5, derivative integral run. And then what you should see now is you should see the same result as your proportional control. Right? Now change the derivative term.
Take this control and replace that with PID. It's not a derived one, it's a derived transform. That's why. Derivative. So first, let's put derivative is equal to 0. And then what you should do is it should give you the exact same result as before. Okay, then now add derivative as 1.
Proportional will be 5.
Proportion will be same as earlier case. And see what happens now. I think it switched your mind. And now, good. So now what? That's good. So notice add the game. Make this game. Increase that to 20. You will notice that once you increase the gate, it should reach that point. So what it means is no matter how much of proportional control you add, your steady state error is not going to go away. But if you add a derivative term, your the steady state error will be minimized. I want you to play with your system and verify that if you add a PID block, so please add a PID block here. PID block here. And I want you to observe this. If KD is equal to 0, no matter how much you increase KP, you land up with steady state error. Then second thing, if you add KD is equal to say 1, if you increase KP to high value, your steady state error, which I'm going to call ESS, can approach 0. Online students, were you able to get some confirmation? Were you able to run this simulation? Yeah, there is a problem. So basically, it's for first order system. I'm going to look at the math in the next 2 slides. But before I actually do the math, what I want you to do is I want you to try to gain some type of physical understanding of how it's working out. So next thing which I want to ask you is remove the step response and add a sinusoidal response. So please remove this step input. Online students, were you able to observe with MATLAB? In the break, I will reset my computer and try to get the MATLAB working and repeat some of these exercises. But please, okay, awesome. Very good, Dhanush. Hunter, Akash,
Shreya. Okay. Now what I want you to do is I want you to take this guy out and put a sign input. I want you to take this off and put a sign input and repeat the same exercise. What exercise are we repeating? First, set the value of D is equal to 0. Then change the value of P, observe the response, and then add the value of D, KD, and see the response. And tell me what you observe. Sine wave, just fine. That should be just input. No, not that. This is the. Yeah. So what's happening?
It's like the graph is shifting first and then wave is matching more.
Okay. So first try with just the proportional control. Increase the proportional control. Observe what happens to the wave output. Then decrease. Then and add KD and observe. Now my quick question to you is, were you able to get exact tracking, which means the output matches with, were you able to get exact tracking? Now the next part I'm going to ask you to do something funny. I want you to match sine output of the system, the input. There will be some combination where they will be very, very close. The gain will be very high at some KD value. Are you with me so far? Okay. And magic?
Like not a lot, but
Very
some
good.
parts.
Very good. Now, what I want you to do is remove the sign and add the step. Or without changing the proportion. Without changing the controller. So in the next part, assuming you got a very well tracking of the sine wave. So what were the constants? 200 for Kp and Kd, 100 and 100. So for Kp is equal to 100 and Kd is equal to 100, the output matched input very closely. And now remove the sine and add a step function, a step input, and tell me if your output matches the input. Pretty close, yeah, but there is some very strict there, but still pretty close. Now what that means is if you have a first order system, and if the first order system is subjected to a step input, and if the step or the first order system is subjected to a sinusoidal input, if you tune the first order system for the sinusoidal input, you can actually get a good performance when the system is subjected to step input. But the converse may not be true. What it means is if you tune your system for the step input and supply sinusoidal input, the system may not exhibit the same behavior. The tracking may not be very good. Everyone understood this? Now what I want to do is, I want to add a dead time to this system. So I want to add the dead time to the system. So how do we add the dead time to the system? Physically, what does this dead time mean? Dead time means your input gets added, but input doesn't reach the output or the system at the same time. So you apply the input, but that input is so sluggish that it takes some dead time to reach the system transfer function. So please understand, I want you to look at your library browser, and there is a delay function. There should be a delay problem. No, not that. Very good practice. This is the delay in zero. Here we are not looking at delay. So we can use that transfer. And add that to input. Yeah, transport. No. And click on the transport delay. It should ask you to change the time. Yeah, change the time delay to say 5 per second. No, just 5 seconds. So, now I want you to see what happens. And you would notice something crazy happen. Add delay to it. Yeah, so something crazy happens to your system. So which means the controller that you have designed, even though it works well for simple PID simple first order system, as soon as the delay comes into the picture, your system is not going to work. All right, we are going to take a break here for 15 minutes. After the break, we will actually spend some more time on looking at a few more concepts and then move on to the lab. So I'm going to stop here and then come back after some time. So just bear with me. I need to restart my computer.